Yes.
Yeah, great. Good. Okay. So you see my presentation, but not my mouse, I think.
No,
Or
we
you?
also see your mouse actually.
Ah, okay.
We see the
Can I
mouse.
Okay, so I'll start. I'll put video also. Hi, this is me. I'm Luca Visinelli. I am currently Grappa University of Amsterdam postdoc with Christoph Weniker. We're working on axion physics, but today I'll discuss about black hole shadows and what we can learn in terms of new physics. I actually will move soon to INFN, Frascati, where I won a Fellini Fellowship, so I'll be INFN for the coming 3 years. So the work that I'm going to present is based on 3 papers that have been published in the last year. The first one being with Cosimo Bambi, Catherine Fries, and Sani Vagnotti, which I will introduce later in my talk. And the other 2 with Sani Vagnotti and also Cosimo Bambi. Okay. So first of all, I would like to make an advertisement about a review on the QCD axiom model that I have worked with Luca Di Luzio, who's currently in DESI, Maurizio Giannotti, who's a professor in Barry University, Miami, and Enrico Nardi, who is in Frascati and who I would be working with once I move to national laboratories there. I also gave an axiom talk last week, which is on this YouTube channel. Maybe you can click on it once I upload these slides to the website. So my outline is to give a brief review about what EHT is. Then I will discuss about black hole shadow, what we can learn from that. So our journey begins here. This is an image of the elliptical galaxy Messier 87, which is also called Virgo A, which is 55 million light years away from us. A close-up look reveals that there are shock waves of material that are being ejected by the center of the galaxy, which we now know, which are due to the presence of a supermassive black hole that's hosted by M87. This is called M87 star, which is imaged here. This image has actually been produced by the Event Horizon Telescope, which is virtually a Earth-sized telescope, since it uses a very large baseline interferometry technique to observe M87 star and also the black hole at the center of our own Milky Way, Sagittarius A, at the resolution of 1.3 millimeter, leading to a resolution of the image of the order of 10 microarc second. So they already had some idea of the image they would have observed from simulations of the accretion disk around the black hole, and from the image reconstruction from simulated data. So they basically tested the pipeline that they used for imaging M87. These techniques are available in their own GitHub. Dot here, the circle, is the resolution that I mentioned earlier, attained by AHT. So this is the picture of the century, the picture of M87, which is associated to this publication from last year. It took 10 days to acquire the data in 2017, plus 2 years of data analysis that includes shipping the actual data to physically to the locations. I have something in the chat. Okay, yeah. This image has been possible because EHT has sufficient resolution. The supermassive black hole is a strong emitter in the radio waves, so it's suitable for radio wave interferometry techniques. And there is little foreground radio pollution. All of this has been discussed in the papers of the collaboration. We see that there is relativistic beaming coming from the plasma. This is why the plasma surrounding the accretion disk. This is why this figure is asymmetric. The mass of the black hole is of the order of 6.5 billion solar masses. And it comes from comparing the image, the actual image of the shadow, with the MHD simulations that I showed earlier. So they have a collection of various simulations, and they try to match the image that fits what they have observed. This mass agrees with what they knew about this black hole from stellar dynamics, and it results into an angular diameter of around 42 microseconds. I'll come back to this. So, of course, the black hole emits Hawking radiation, which is nevertheless unobservable. Then there is other indirect evidence that we can gather and which is needed, that comes from the motion of nearby star, radio, and gravitational waves. So there is a whole plethora of different signals for multi-messengers astronomy to be gathered from this. So what is the shadow of a black hole? It's this dark dot in the center, so it's the dark area in the image of an optically thin region around the compact object. Why the image appears like this? Because the shadow of a black hole is basically the photon capture radius. So here I have a non-rotating, so Schwarzschild black hole, for which, given the gravitational radius, which is basically the mass of the black hole converted to units of g over c squared, I can define the Schwarzschild radius as twice this rg, which is the black dot here. Then the photon capture radius, which means the orbit within which any photon that comes from infinity would eventually be captured by the black hole and ending into the Schwarzschild radius. Well, this radius is of order square root 27 Rg. So it's larger than the Schwarzschild radius, and also larger than the photosphere, which is the radius at which there are stable circular orbits for unstable circular orbit for the photons. So given this radius, twice this radius would basically give the size of this shadow, and twice this radius over the distance of the black hole to us gives the image angular diameter. Now I have to match this angular resolution, angular measurement of 42 microsecond with my theoretical expectation, and we find basically that the number 42 microsecond is obtained for a supermassive black hole of mass 6.5 billion solar masses. So this is basically the method by which you can assess the mass of the black hole from comparing the size of the shadow with what you actually observe and using this formula. For a rotating black hole, so here we're talking about a Kerr black hole, the size of the horizon is actually different, and in particular we have it depends on A, which is the spin of the black hole, which is capped by the fact that it cannot be larger in units of gravitational units than the mass of the black hole. So once I convert the spin of the black hole in units of masses, A cannot be larger than m from this formula. This is just a prediction of general relativity. Kerr black holes cannot have a indefinite spin, but the value of the spin per mass has to be smaller than the mass of the black hole itself. Given this, the trajectories of the photon, which is what we see in the figure here, are just dependent on two quantities, which are the black hole spin and the angle of observation at which we observe this this black hole shadow. The observation angle is actually the angle between our view, line of sight of, between us and the black hole, and the axis over which the black hole rotates. So this photon geodesics, where r is the distance of the photon from the black hole and lambda is a affine parameter, define the bound orbits. So for a non-rotating black hole, we expect our shadow to be circular because of axial symmetry. But for a rotating black hole, we actually observe a distortion that depends on how fast this black hole rotates. These figures are obtained for an observation angle of 90 degrees. Why we have such a distortion? It's because of spin-orbit coupling. So once we define the distortion as the deviation from a circle over the mean radius of the shadow, we see that this quantity is non-zero for a rotating black hole, and that actually depends on the observation angle, theta ops, and on the spin of the black hole itself, because of the spin-orbit coupling between the photon and the black hole spin, which for gravity is opposite to what you expect from electromagnetism. So it is repulsive if the two spins are aligned, the spin of the photon and that of the black hole. So we learned that inclination also matters. So the size of our distortion, delta, depends on both the spin in units of the mass, which is on the y-axis, and depends also on the value of theta. So if I reduce my observation angle, I have smaller and smaller distortions depending on the value of delta, for a given value of delta. So that when I have theta equal to 0, I don't have any distortion because I observe the black hole from top. So what do we know of M87 star? We can learn something from the accretion disk and the jet that come out of the accretion disk. So on the left, we have a estimate of what theta ops, so the observation angle, the inclination angle of the axis, is expected to be for M87. This comes from considering the jet, which depends on two parameters, R and beta. In this paper, they take these two quantities basically they take two rather extreme values of this quantity, and then they look at the value of the boost as a function of theta, and they find a sweet spot in which theta is expected to be over 17.2 plus or minus 3.3 degrees. Instead, for A, we only have a lower bound. So we know that A has to be larger than 0.4 in the case of prograde spin, or 0.5 in the case of retrograde spin. So this is assuming that the accretion disk has some infall profile. So now let's go to the AHT paper. So they mentioned two things over which our work is based. The first one is that they measure the deviation from the circularity, which they define as the root mean square distance from an average radius in the image. So they define an average radius of the shadow, and they look at how much their figure differs from this circle. And they find that this differs at less than 10% from a circle. So we use this information, and in the paper with my collaborator, Cosimo Bambi, who's a professor, full professor in Fudan, Catherine Fries, who's a full professor in Austin and Stockholm, Sunny Vagnosis, who's now in Cambridge as a postdoc student, we defined the deviation from the circularity, delta C, exactly as what the AHT paper says. 1 over the mean radius times the deviation over the circle of the image itself. Using this formula, we scan over the parameter space of the rotating black hole, which, as I said, it comprises of the spin and the observation angle of the black hole, and we compute delta C for different expressions for the shadow, and we obtain that in this corner of the parameter space, in which A star is the spin over the mass of the black hole. So for black holes that rotate too fast and which are too much inclined with respect to us. Well, in this corner of the parameter space, the circularity would be too large. So we exclude this smaller fraction of the corner. This is, of course, in agreement with the claim that the theta is of the order of 17 degrees, and that A star is expected to be larger than 0.4 for prograde and 0.5 for retrograde. We can do much more than this, of course. This is just a warm-up. So can we test the physics beyond GR? So Cosimo Bambi and Katie Fries 10 years ago studied what could be a possibility to go beyond Kerr space-time, Kerr solutions for black holes by assuming that we can have a solution with A stars larger than 1. So this would be that super spinor objects. So these are not Kerr black holes because they violate the Kerr bound. But nevertheless, there are solutions to the Kerr space-time for which A star can be larger than 1. How do you find these solutions? And notice that the EHT paper says that these systems, these objects, will have a shadow which is too small and not enough circular than what they see. So they exclude these objects. But we look at this claim more carefully. So, what are superspinors? We mentioned that for a Kerr black hole, A is smaller than M. Because this is basically because A larger than M has a naked singularity. So the idea is that to cover the singularity by some quantum gravity theory. So we basically say that GR works down to some radius R, below which GR breaks. It is replaced by something else we don't know. We know it is some quantum gravity. And this R basically gives a sort of effective parameterization of the quantum gravity effects. But it's a new parameter in the theory. So we can solve for GR only in the region beyond this superspinor radius. And we treat this with this new parameter as a variable that has to be assessed against our image. Doing so, what do we learn? So first of all, we mentioned that Kerr black hole shows a shadow which is rather circular for the case of a small inclination, and it then bends and distorts if the inclination is larger. Instead, for a superspinor, we observe a shadow which is too small and too flat, oblate, in the case in which this superspinor radius is small. And this is basically the case that EHT collaboration took into account. This shadow is too small compared to what we see. But if you explore the parameter space, we actually find cases for which, for given observation angle, for given spin, and for given radius of the superspinor, the shadow for a superspinor is circular and large enough so that it matches that we see. So basically, there are regions of the parameter space for these exotic objects to also match what we observe. And this is basically what we explored. We fixed our A in this case to be 1.1, and we looked at the region of the parameter space theta versus radius of the superspinor, and we find that, well, this green hashed area is the area which is allowed. So for the black region here, anything that's to its left is allowed, where the black region corresponds to the region for which the shadow is circular enough. So anything to the left is here is a superspinor that is circular enough. Anything within these green curves is wide enough. So this hash region is the combination of the two. So we could have super spinors with some observation angle of order 10 to 20 degrees, spinning faster than a Kerr black hole, and with a radius of super spinor large enough so that it matches the same shadow as what we see. So this is my conclusion. So, okay, this was just the first paper we discussed in terms of black hole physics. What I wanted to do is to warm up and with this type of computation. What I want to do now is trying to merge what I learned from black hole with what could be coming from light bosons, for example, or testing new physics using this type of techniques that I try to improve in the future. Thank you.
All right. Thank you very much. So, are there questions from the audience? Sorry, I cannot hear you. Maybe it's your microphone.
You can type if the microphone doesn't.
Sorry, I can go ahead in the meantime while the question is being typed.
Okay.
So I think a key point for the EHT collaboration to constrain some exotic compact objects is not just the shape of the shadow, but the lack of a jet launching mechanism. So for a Kerr black hole, you of course have the Penrose process in the ergosphere that is a viable jet launching process to explain the jet that is in fact being seen in the X-ray. So if you're looking at different exotic compact objects, I think this is a key constraint to take into account. So in your case, did you think about that?
Yeah, well, yes, it's in the to-do list because you have to redo the numerics. So I didn't include this in this first paper, which is just speculative. Yeah, but it's something that we basically thought to do in the. I agree. This is not the main. The shadow is not the only reason why we think that M87 star is actually a Kerr black hole, and not something more exotic like a boson star or a super spinor.
Other questions?
I think something will be typed.
Okay.
Well, meanwhile, I have a question too, if you're waiting. Shall I go for it?
Sure.
So, Luca, you mentioned it a little bit at the end in your conclusions. In principle, if you have a light scalar around, you expect that you can have hair for the black hole, right? And yeah. Maybe in principle, you should be able to see something at these things. Any comment on that?
Well, well, there have been papers about yeah, there have been papers about what how you can use black hole shadows. The point is that to observe light bosons. So we know that a rotating black hole might have a Bose-Einstein condensate around it,
yep,
which emits gravitational waves and would also distort the shadow. The point is that these objects, this would be observed, could be observed only, would be interested only for stellar mass black holes, given what we know. So this is something I want to check, because I haven't done the computation myself. I just read a couple of papers, but I think there would be something more to learn. So this is my only comment. It's this is something that I want to work on.
Okay, thanks.
Sorry, can I ask a follow-up question to that? Sorry, it's John here. Why do you say that it's only interesting for stellar mass black holes and not galactic center mass black holes? I mean, the superradiance process, which builds up the Bose-Einstein condensate, is still possible for the supermassive black hole.
Yeah. Well, yeah. So that was the claim of the paper. So basically, the Compton length of the boson has to be of the same size as the.
Yes, of course. Yes. Or sometime in the past it had to be. Yes, but yes.
Yeah, exactly. And I think that for a supermassive black hole like M87, this corresponds to ultralight axion, 10⁻22 electrons, which is quite interesting. But I've done a little search on the literature. I haven't found that. This is why I think
Sorry, but I'm a bit confused what you mean by you haven't found that.
I haven't found a paper that discusses supermassive black hole and Bose-Einstein condensation. And
yes, absolutely, there it is. I mean, it's in my original paper with Savas and Mina and co.
Okay.
And so, but it's also in the later papers, the follow-up ones of Mina and Sergey.
You go on black holes of that mass.
Oh yes, most certainly.
Okay.
There's a whole range. I mean, for instance, as you make FA higher and higher and higher, and you lower the and you make the instanton action larger, you move down to that region. So most certainly you have an interesting region there.
Exactly. Yeah. It's interesting because of.
Yes. You're not saying you're not saying in principle. You're just worrying about whether there was candidates there. Of course, that's always an issue, but it's logically possible.
No, candidates, absolutely. If it's a ULA, it's interesting candidate.
Yes.
What I mean is that I haven't seen papers in which they discuss the shadow that would be originated from such a system.
Oh, well, that's an interesting separate issue, yes. Yeah.
And how could you detect it? How could you? How would you see it? And
well, seeing as in principle, you can put about roughly about 10% of the original mass of the black hole in that cloud. I mean, that's and you can put it typically at that radius, which is sort of r equals 3 to 5m, that sort of range. You should have significant effects. I mean, you should at the few percent level, you should have effects on the shadow. Maybe not 10% or bigger. I agree.
Okay, I have a question here from the chat. Okay, from Hoofman Davodjelas. It says there is one that it's a comment. Paper that discusses M87 star, which is 1904.09242. Okay, I'll save this.
Hi, sorry, that's kind of a self-promotion, but in case you're interested.
Okay. Yeah, and Sunny Vagnosi is actually mentioning the paper that I read recently. Okay, thanks, Sunny. Okay, so I'll save these two papers. Okay, thanks for the attention.